Okay, with our newly acquired deep understanding of the RTLOLA type system, let's come up with a specification for an interesting mission statistic. Suppose we want to compute the correlation between the distance between waypoints and the relative path deviation we experience when traversing those waypoints. The first thing we have to do is define the input streams, and for this we have the WP stream for waypoints and the position. Now suppose we only get a new waypoint when we reach the last one. Now the first output we want to compute is the distance between two waypoints. For this we take the absolute difference between the current value of the WP stream and the last one. And note that WP dist is the timing of WP dist is coupled with the timing of WP. Now the next thing we want to compute is the total distance we have traveled so far. For this, we take the current position we have and subtract the last position we got. So this is the delta in the position, and now we sum this up in the stream by referring to the last value of total dist with an offset of -1. Okay, now the timing of this total is bound to position. So whenever we get a new position, we compute a new total distance, which makes sense. However, when we want to compare the distance between waypoints and the distance we have traveled so far, we have to somehow come on a common denominator for the timing. And for this, we define a new stream, and this stream is the total distance at a waypoint. And the timing of this stream is bound to waypoints. So whenever we reach a waypoint, we want to see what is the total distance we have traveled so far. And to access this stream, we need to have an asynchronous lookup. In this case, we use a hold operation where the default value would be 0. So now we know that the stream total distance at waypoint and waypoint distance work on the same timing. Okay, so the next thing we want to compute is the deviation between those two streams. So we take the absolute difference between two components. The first one is the distance between two waypoints. And note that here we have to access the last value of WP dist, because we only compute a deviation at points where we get a new waypoint. And we don't need to use the distance from the current position to the next waypoint, but from the last waypoint and the position we were before that. So we use the offset operator to get the last value of WP dist. And the second component of the difference here is the distance we traveled to reach the current waypoint. So for this, we take the current total distance at a waypoint that we have traveled and subtract the one we had at the last waypoint. And this is the difference in the total distance we traveled between the last waypoint and the current one. So the absolute value then gives us the deviation from the optimal flight path we had. Okay, now we do have the deviation and we have the distance of waypoints. And we want to compute the correlation between these two signals. So we first have to define one stream containing the information for both streams. So we define a new output, distance versus deviation, where this is just a pair of the WP distance and the deviation. And the timing of this stream, once again, is bound to the waypoints. Now we want to have the covariance between those two streams. So we use an aggregation function that is indefinite. So it has the infinity symbol for the over duration. And we use the covariance aggregation function. Similarly, we compute the variance of the distance stream and the variance of the deviation stream. And now that we have these three values, the only thing left to do is compute the correlation. And for the correlation, we take the covariance and divide it over the standard deviation of the deviation stream and the distance stream by just squaring the variance. And that's it. That's how we compute the correlation here. And of course, this is just a value, and we could then again define triggers to see what we can do with this value. The main takeaway message from this specification here is that we have seen a couple of interesting things we can do for sensor level specifications. And this is a mission level specification. And here we once again have primitives to express these abstract and mission level properties quite conveniently. And okay, that's all. Now we have the specification, we run it through the type checker and it's happy. So we got a spec. Now what do we do next? And there's two things I still want to discuss. First, we want to see how to further increase the confidence in the specification. And second, we want to analyze the complexity of it to some extent. So we want to know what is the memory consumption and have a rough idea of how long it would take to evaluate the specification. Now, to further increase the confidence, what we do is we want to validate a specification using interpretation. And there's a key thing here. When developing a cyber-physical system, it's not like we fully develop the system and then we deploy everything and run a first mission. That's not how it works. Before that, we have test runs, and these test runs are in controlled environments. And here we check how does the system behave under certain circumstances. And this information of the sensor readings and everything is recorded. These records can then be used for the validation of the specification. So here we take such a log, we manually annotate what should happen, what should the monitor report at certain points in time. And if we then have an interpreter for the specification, then we can just use the interpreter, give it a specification and log, and see what happens. And such an interpreter was presented at CARF last year. And here we had a specification where we checked for GPS frequencies. We detected jumps in the GPS IMU module, and we detected hover phases. So the specification was not really trivial. And still, if we had a log over 430,000 events, we evaluated everything, and the interpreter needed around 1.5 microseconds per event, running at 146% processing power. The stack size here was less than 1 kilobyte and required no heap. The main part here is that the interpreter didn't need any specific hardware architecture. So it was not run on hardware, it was run on any machine. If your machine can run C code, then your machine can also run the interpreter. And the running time is remarkably fast and sufficiently fast to enable rapid development. So the idea here is that if you have a specification and you have these log files, you can just check whether the specification makes sense on these files. And this allows you to have a couple of test runs for your specification, and this greatly increases confidence in the spec again. So that's quite neat. The second thing was the specification analysis, and for this we first compute the dependency graph of the specification. And what you can see here is the dependency graph for the waypoint specification. And in the dependency graph there are a couple of different arrows. So these solid arrows here indicate that there is an axis, here in this case with an offset of -1 or an offset of 0. This arrow here is a sample and hold operation. And these thick lines here indicate sliding window aggregations. So when looking at the specification, at the dependency graph, we can see a couple of things. We know sliding windows are more expensive than normal lookups. So the more of these thick lines you have, the more intense the computation is. And also the longest path through the dependency graph indicates the worst case time your monitor is going to need for an evaluation. So that's already a certain indicator of the complexity of the specification. And then we want to analyze the memory consumption of this spec. So what we do for this is, for each single stream in the dependency graph, we can compute the number of values we have to store of this stream. So for example, if we take the position stream here, we know there's an axis with offset 0 and an offset of -1. So this tells us that we need to store two values of the position, the current one and the last one. Since we know that by the value type of the position that every single value has size 128 bits, and we need to store two values, then the memory consumption of this stream is 256. And this is something we can do for every single stream. Of particular interest are the sliding window aggregations here, because depending on the duration of the window and the aggregation function, we need different intermediate values we have to store. Here in this case, the computation is for the covariance and variance. They are rather simple, especially because it's an indefinite integrals, and those are simpler than non-indefinite non-indefinite sliding windows. So in this case here, we just need two 64-bit numbers as intermediate values, and that's something we have to add to the memory consumption of the stream. So in this case, the total consumption of the stream is 192. And the memory consumption of the monitor as a whole is then just the sum of these values. So in this case, we need 1500 bits of memory. Okay, so this way we have a static bound on the memory consumption of the monitor, and we know for a fact that this bound will never be exceeded by the monitor. That's pretty nice. And this analysis also finishes the RTLOLA block, so our first block. To summarize briefly, we have seen that there is a spectrum of different specifications and properties. And depending on where in the spectrum we are, we have different requirements on the monitor. And we have to pick a language and a monitoring framework that enables to monitor this particular specification. We have seen that RTLOLA is suitable for a lot of different specifications, but not for everything. So for example, the specification here is not expressible with RTLOLA because it requires more memory than RTLOLA would allow. So here we would have to resort to a different specification or work with an under approximation of the property. We have seen that RTLOLA has a strong type system that helps the specifier in having better understanding of the specification and also having an increased confidence in the correctness of the specification by detecting inconsistencies within the spec. And lastly, we have seen that there is an interpreter for the specifications, which further allows us to increase the confidence. And there are analyses that allow us to have an idea of the complexity of the spec. And this finishes the first block. Now you once again have a chance to ask questions until we continue with block 2.